beetle. This ground beetle is illuminated by a single light source. Person's taking a picture of the bug, and it's actually brown or black. And look, the light spreads out into a rainbow, okay? And it looks like it spreads out. If you look at the different angles that we have here, we had blue on the inside, red on the outside. Check it out. I get the light, it's like spread out into a rainbow here. And this is coming from a diffraction grating on the back of the beetle that runs this way. And so it ends up spreading the light out into a rainbow because of the diffraction phenomenon. And it's got structures on its back that make it do this. Now this is really practical. This is really practical. Here's another picture. And you can see this is a close-up picture of the back of the beetle. And you can see here's m equals 0, m equals 1, m equals 1 on either side. And you can see it's a rainbow. So when you look at this bug, what color is it? Well, it's like rainbow colored. And it's also looking diffuse. It's kind of like hard to tell the edges here. And it's fuzzy, like looking at things through the rainbow glasses. And that's why, when you look at this beetle under this light, okay, what color is it? Well, it kind of depends on what angle it's at. And if it tips like this, the color it appears to be is going to change. And the reflection isn't sharp. It's kind of like fuzzy. And so as a consequence, it's hard to spot. And the main reason why people suspect this is useful is for protective coloration. I had a situation a number of years ago when I went down to Belize, and I went to this butterfly place. And this guy was telling me all these stories about the great conservation efforts that he does, and he's very proud of it, and he's proud of his work with school children, and I work with school children, he works with school children. But I was like trying to get a video of a blue morpho butterfly. The blue morpho butterfly's got these amazing structures on its wings that we'll talk about. And when it tips its wings at a different angle, it changes color very dramatically. And I thought, I want to get a video of this to use in my class. So I would get my video camera. I'm taking a picture of the butterfly. And the butterfly would move its wings, and its color was changing. And then it would like take off, and I would lose it. And it'd be like, I'm taking a picture of the butterfly, and it's like, it's gone. It's out of the, I've lost it. And then I would see, like, maybe it's me. So I'd take a picture of a red butterfly. Red butterfly is flying away. I'm doing this. And I'd say, OK, now I'm going to try the blue morpho. I'm looking at it, and then it's just vanished. It's like gone. I couldn't follow it. And I was getting really cranky. And this guy is trying to tell me about all this great work he's doing. And I'm just getting like totally cranky. And it's like, shut up, whatever, about your whole program, the good you're doing. I don't care. I'm trying to take a picture of this butterfly, OK? And I think I tried to make it better after that. But anyway, it was really remarkable. And it showed dramatically the whole point of this structural color. It's extremely protective. Because my brain was trying to follow this thing. It was blue, and then a tenth of a second later, it was brown. And my brain said, forget it, different thing. And I couldn't track it. I could not follow these things. And I realized my inability to get a video illustrated the principle of protective coloration better than the actual video would have, although not nearly as satisfying. So I don't have a video to show you because it works so well. It's fantastic. Now, here's another picture of a beetle. And you can see light shining on it, first order, second order, third order, and the light is broken up into the spectrum. And it's very, very good. And actually, your top changes color with angle. You've got protective coloration, too. Sweet. Is that why you do this? Yeah. So you're talking to someone, and you need to evade them, and you can just tip, and it's like, whoa, where did you go? Sweet. But we can do a calculation for this. And here's numbers from a paper. I actually went and looked up research papers on this. So ground beetle, illuminated of light with lambda is equal to 570 nanometers and produces clear maxima at 13 degrees and 25 degrees. What is the spacing of the lines in the exocuticle that produces this diffraction effect? That's a big word, isn't it? I was really proud of myself. I got that out of the paper. But no, it just means it's got on its back, it's got these structures, and it's got lines, okay? And the lines produce a diffraction phenomenon. And you can see it. Look at this one. You can see there's a rainbow red, and then there's blue, and the light goes from the red to the blue. It's just like the rainbow glasses, but it's on the back of the beetle. And what relationship do we use to solve the problem? Heavens to Betsy. We use the same one that we use to solve diffraction grating problems, because a reflection grating is a diffraction grating. And so we use this relationship right here. Light comes in, hits the back of the beetle, light comes off. And I have light that comes off at two different angles. Theta 1 for my first order fringe, 13 degrees. Theta 2 for my second order fringe, 25 degrees. And I get clear bright spots at those angles. Now let's look at our relationship here. D sine theta, it's actually theta m. It's the angle that corresponds to a particular order of the diffraction. Okay? M is the order. Theta m is the angle that corresponds to the mth order. Lambda is the wavelength of light. D is the spacing of the grating. That's what we're looking for. We're looking for the spacing of the lines on the back of the beetle that produces this effect. So that's what we're trying to solve for. Here's the thing. I've got two pieces of data. I've got a theta 1 and I've got a theta 2. Theta 1 corresponds to m equals 1. Theta 2 corresponds to m equals 2. And so I can solve this equation two separate times. First off, let's do m equals 1 first order. I have this. D is equal to m times lambda divided by sine of theta m. Okay? So for m equals 1, m is equal to 1. Lambda, 570 nanometers. So 570 times 10 to the minus 9th meters. Theta, 13 degrees. And if I do that calculation, I get to 2.5 times 10 to the minus 6th meters. But I can also calculate for m equals 2. For m equals 2, I get d is equal to m times lambda divided by sine theta m. But m is equal to 2. Theta is equal to 25. And if I work that out, I get to 2.7 times 10 to the minus 6th meters. So if you're the investigator, what do you report as the spacing? 2.5 times 10 to the minus 6, 2.7 times 10 to the minus 6, 2.6, go with the average. In fact, that's what they reported. That's what they estimated the spacing was, 2.6 times 10 to the minus 6 meters. And then you can back this up and say, let's go ahead and look at this insect under an electron microscope. And if you do that, you can see that you get a spacing that corresponds to essentially what you talked about. And so there really are structures that do this. And it's very practical.